Hello. In this video I just want to go over a couple other periodic trends. So before we talked about atomic radius and ion radius or ionic radius. So in this one I want to talk about melting point. Now melting point has a general trend where it will go up, so ever so slightly between groups 1, 2, and 3, and 4. And then it will start to go down again. So if I look across my period 3 here, then we'll see that the melting point for sodium starts off actually relatively high, and then we have a melting point for magnesium. It's also a little bit higher. Aluminum is higher still. Silicon is actually very, very high, and then we see it drop down again with actually phosphorus, then sulfur, chlorine, and then finally argon at the beginning. So we have a general increase and then a decrease. And this is because of the bonding types involved in each one of these elements, so how they bond to themselves. So the first three are metallic, so they have a metallic bond. And with a metallic bond, the more outer valence electrons there are, the stronger that bond is. So sodium only has one outer valence electron, and it also means that if I get a little smaller here and I move this over, so if I'll draw sodium here, in a sample of sodium like this, 1 plus, 1 plus, 1 plus. Let's draw it real quick. It will only have one electron to donate to its metal bond. So it will only have one electron that will kind of bond everything together. Magnesium, it will have 2, and aluminum will have three electrons. So when it bonds to itself, and this metallic bonds, it's very, very thick. This electron cloud, it's called, or electron soup, and bonds everything together. So we see the trend of melting points go up because sodium has 1 electron in its outer valence shell, magnesium has 2 electrons, and then we have aluminum, which has 3 electrons. Now it all changes at silicon, because if I move everything down, zoom out again, silicon actually is rather unique, and when it bonds to itself, it bonds kind of covalently in this kind of tetrahedral kind of way, and this kind of goes on for infinity. Let's do that guy. So it kind of goes on to infinity, and because of this, it forms this like kind of giant covalent structure, which is very, very very hard, but also it's actually very, very stable. So the energy required to break it's a lot, and because of this inherent bonding between all these other silicons, and it like extends out pretty much to infinity, that means that silicon is strong. So it takes a lot of energy to break apart these bonds, thus it has a high melting point. So the melting point, it is equal to the energy to break the bonds. So as soon as then we get to phosphorus, and I'll move all this stuff down. So phosphorus, P will generally just be bonded to three other phosphoruses like that. Sulfur, well, it forms kind of a crown. That's why sulfur you tend to see has a slightly higher that's the wrong thing, sorry. Slightly higher that. Slightly higher melting point than phosphorus because it's a bit bigger and there's inherent forces in that. Chlorine, well, just a diatomic, so ClCl. And then argon, well, it's just a lone atom, so it's all by itself. So you see the melting points change over time. Now the second thing I wanted to bring about is reactivity. Now reactivity, if I just kind of get rid of this, break all of this off, and I can zoom this out like so. So reactivity works like this. Ignoring my noble gases, for metals, from lithium on down, the reactivity goes like this. But for my halogens, my group 17 guys, well, it goes like this. And there's also a general trend in reactivity this way and also this way. And we see this trend in reactivity because for the alkali metals, well, it's mainly due to how strongly it can hold its outer electron. So it is related to ionization energy, which in turn is related to the number of shells, and it's also related to the shielding effect of the inner core electrons. We see this trend in reactivity with our halogens. It's related somewhat to electron affinity, but it is more related to the effective nuclear charge, or the ability or the strength of the protons holding on to the electrons. So in the case of fluorine, it holds onto it strong, and it will want that extra electron more than all the others just because of the charge density within it. And so as a result, like the easiest kind of thing to react would be fluorine and francium. So francium fluoride would kind of be the strongest thing to react. And this reactivity kind of leads to a kind of reactivity series in that if I was to react a couple things together, one would replace the other. So if I have lithium chloride and I react it with F2, I'm going to get lithium fluoride. And balance it out to 2 and chlorine gas. Essentially what's happened is fluorine has taken the electrons because it is more reactive, and that's why it's going to take those electrons. It wants them more, and that's due to its effective nuclear charge. But if I was trying to react, say, to lithium chlorides plus bromine, we wouldn't get anything. No reaction, because bromine is not as reactive as chlorine, so no reaction would take place. And this leads into how we kind of determine whether or not they're more reactive or not. We can just kind of test them out, but the main idea is how much they want those electrons, or in the case of the alkali metals, give them up. So again, a lot of these things come down to the energy and how tightly they hold on to the electrons or want to give them up.